I got cut off again. I forgot to keep track of time, and this program limits me to 15 minutes. So, we were back on what sperm cells this male can make. He can make these, wild type, and he can make Y chromosomes which do not carry the gene for eye color. So when we look at the F2 generation, we can see that this cross, the probability of this cross is 1/4. 25% of them, they would be female since they are XX, and they would be heterozygotes. Actually, no, they're not heterozygotes. This is a typo here. There should be a plus right here for this W. Homozygous dominant female, or homozygous wild type females. Here we have a wild type male. Here we have heterozygous females. These females are now carriers, and this is where the white eye shows back up, and you can see by this cross that the only way that that can show up is if this individual down here in the bottom right hand corner is male. Alright, so in humans, let's take a look at these sex-linked genes. Okay. I'm going to pause for a second. I'll be right back. Okay, I do want to go over how these are produced in humans. Okay, so males produce sperm. Since males are XY, they have 44 chromosomes that are autosomal, plus the X and Y chromosome that are the sex chromosomes. So they produce haploid sperm cells that can be 22 plus an X or 22 plus a Y for our 23rd. And then if fertilization occurs with the X chromosome, the zygote is female. If it occurs with the Y chromosome, the zygote is male. The only thing that females can produce are eggs that are 22 autosomal chromosomes plus an X chromosome. So it is the male that determines the gender of a child. Tell that to Henry VIII. It was his fault that he couldn't produce any male offspring. The sex chromosomes then have many genes that character for things that are unrelated to sex. We're going to take a look at some of those from your reading. We call those genes sex-linked genes. Sex-linked genes. And usually, in humans, these are usually carried by the X chromosome. They follow that very specific pattern of inheritance that Morgan discovered. For a recessive trait to be exhibited, the female needs 2 copies of the allele. The male, however, only needs 1 copy of the allele. This is why sex-linked traits are more common in males than they are in females. So let's take a look at how that works. This would be how it works for any trait. Here we have, this is how you write this, okay? So you write X capital N for dominant, X capital N. X lowercase n would be for the recessive allele. And if this is male, then you write Y. So the sperm that could be produced are X little n, Y. And the eggs that can be produced from this mother are X big N or X big N. So sometimes you don't even really need this bottom box, since the only egg that can be produced is X big N. So these are the possible outcomes, right? You've got a 50-50 chance of being heterozygous. If you're a female, you have a 100% chance of being heterozygous rather than 50-50 chance. But if you're male, you have a 100% chance of not having the disorder. These are now carriers, right? So this is what would happen if a carrier bred with or had a child with a normal male. So the sperm that can be produced are X with the dominant and Y. And here we can have X dominant or recessive. So the female children in this case would be either homozygous dominant or they would be carriers. The male children have the possibility of being the dominant, having the dominant gene in their X chromosome, or having this condition. For females to have this condition, this has to be the pattern. So the mother has to be a carrier, or she has to have the condition, and then the father has to have that genetic condition. So the sperm that can be produced are a sperm that has the recessive allele, X little n, or a Y chromosome. And then if that fertilized an egg that was dominant, you would get a heterozygous female, or a 1/4 chance of having a heterozygous female, or a 1/4 chance of having a normal male. Now, since the egg can be produced from this, you would also have a 1/4 chance of having a female with the recessive condition, or a male with that recessive condition. So what are some things that are caused by these recessive alleles? Okay, so we have color blindness is one example, not on your reading, but it would be a good one to talk about. Color blindness works exactly this way. Now, my son is colorblind. I am not colorblind, and his mother is not colorblind. So which one of these three examples works for my third son? Think about it for a second. I'll give you a minute to think about it. Not a minute, but a few seconds to think about it. Like Jeopardy. I'm going to stop now, because that probably sounds horrible. Which one? It would be this one. If you chose this one, you are correct. His mother would be a carrier, and I am not colorblind. And so he was a 1 in 4 chance of being a colorblind male. 25% chance of being a colorblind male. Now, how would his mother be a carrier? She could have inherited that if her mother was a carrier, but it turns out that her father is colorblind. So he is the one that passed that on. Since she is not colorblind and her mother is not colorblind either, we know that this X little n had to come from her father. So that's for colorblindness. Duchenne muscular dystrophy and hemophilia work the same way. So if we went back to this, people who have hemophilia, males would be X little n, females would have to be X little n, X little n. If you think about the royal family, it was Queen Victoria, right, where hemophilia was passed on to her son. They got that from her because she was the carrier. The dad had a normal version of the gene, so it would have been this example right here. And none of the female children got hemophilia, so they got the X big N from their dad, from their father. If their father would have had hemophilia, then they would have been more like this chance right here to have hemophilia. And Duchenne muscular dystrophy works the same way. It's a neuromuscular degenerative disease where you get loss of muscle control because of the recessive disorder. And it's linked on the X chromosome. Okay, the last concept we're going to cover is X inactivation, and I'm going to watch my clock. I got 6 minutes to talk about X inactivation. I probably won't take the full 6 minutes. So let's take a look at that. This only occurs in mammals. So in mammalian females, one of the 2 X chromosomes is randomly inactivated during embryonic development. The inactive X condenses into a chromosome known as a bar body. And it condenses so much that none of the genetic information can be read from that bar body. If a female is heterozygous for a particular gene located on the X chromosome, she will be a mosaic for that character. And it was kind of interesting that I was talking to Mrs. Goff today about this, and I'm going to tell you a story after I go over this example. The calico color in cats can be described by X inactivation. So what happens is these are the two chromosomes. She's a heterozygous for both of those. So she has the allele for orange fur and the allele for black fur. And again, they're carried on the X chromosome. The patches of her fur that are black have an inactive orange fur chromosome. The patches on her fur that have orange have an inactive black X chromosome in those cells. Now, male calico, there are a few male calico cats, but it is really rare because they have to inherit a disorder that comes from non-disjunction. Remember when we talked about non-disjunction? Non-disjunction of the X chromosome in either a sperm or an egg will result in a male cat that is XXY. XXY. So the X inactivation still occurs, and since the gene causes the, or since the X inactivation occurs, they can have the same pattern of fur color in a male calico cat, but that is a very, very, very rare occurrence. First of all, they have to have that non-disjunction and have the XXY syndrome, and they also have to be heterozygous for orange and black fur at the same time. So sometimes if you have a male calico cat, maybe you could try selling it on eBay because they are very rare and make a lot of money with it. I don't know. That would be kind of rude. Okay, for my last thing, let's talk about Mrs. Goff. Mrs. Goff has one eye where the iris in her eye is partially blue, and other patches of cells are brown. So she's got patches of blue in her iris in one eye and patches of brown in her iris in one eye. And I believe that that is caused by this same thing right here. So she would have one X chromosome with the allele for blue and one X chromosome for the allele for brown. So in the cells that are brown, the blue gene was inactivated, and in the cells that are blue, the brown gene has been inactivated, and so she's got various patches on there. All right, well, that is it for today. I hope you have enjoyed the screencasts as much as I have enjoyed making them. Study for the test. Email me your questions. Your substitute teacher is a microbiologist, so she might be able to answer some of your questions about heredity. And good luck on the test. I will see you guys when I get back from my conference. Hopefully I'm going to learn lots of awesome things about how to be a better teacher and how to help you guys to get ready for the AP exam and pass that. And everything will be wonderful and sunshine. Thank you. Goodbye.